Hello and welcome. This is going to be our lecture video from March 1st through 2nd. Go ahead, get on your notes, copy down the following rational function and attempt to factor it. You can pause the video here if you want to do it on your own, but here's how we would do this. First, in the top polynomial of this rational function, I notice everything is divisible by 2, so I take on a 2, leaving behind an x squared plus x minus 2. I divided 2 out of each of those terms. And on the bottom, no greatest common factor, so I can begin to think about simple factoring and what two numbers multiply to be a -5 but add to be 4. Two numbers that multiply to be -5 but add to be 4 are going to be a +5 and a -1. All right, that gives me -5 and a 4. All right, on the top, now I can factor this quadratic, again using simple factoring. Two numbers that multiply to be -2 but add to be 1. Let's see if we can think of those. So multiply to be -2 but add to be 1 is going to be a +2 and a -1. Multiply to be -2, add to be 1. All right, that is factored. Factoring is often the first step in graphing these rational functions or identifying important features of these rational functions. Our goal for today is to better understand what causes vertical asymptotes and holes in a rational function graph, as well as to find the equation of slant asymptotes. Why are we doing this? So we can tell where the important features of a graph are going to be before we graph it. Or you might not even need to graph it if you just need to know a specific spot like an x-intercept. All right, so vertical asymptotes and holes. So these are both types of discontinuities. So they are both types of discontinuities. A vertical asymptote is represented by a vertical dotted line on our graph. And our function has to get around that, we could sometimes call it a wall, and it can either go up and under or under and then over. So typically our function is staying close to some sort of horizontal asymptote until it reaches the vertical asymptote, then it goes under. If it goes down to -infinity, it'll reappear at +infinity before coming back and trying to reassume that horizontal line. All right, a hole is a little bit different. In this scenario, our graph is just going along in a continuous fashion. It can be curving up or down, but at a very specific value, all right, we skip just one number and then keep going. All right, vertical asymptotes, these are caused by factors on the bottom that don't cancel. All right, holes are factors that do cancel. So you'll have the same factor in the top and the bottom, and you can cross them out, but the value that makes that equal to 0 will still cause a hole in our function. So, for example, if I have the function y equals x plus 1 times x plus 2 over x plus 2 times x plus 3, I can cross out these x plus 2's, but just because I cross them out doesn't mean they don't impact the shape of this graph. At exactly x equals -2, we will find a hole in our graph. That's the value that makes this factor equal to 0 and will result in a 0 over 0 expression, which is undefined. And then at x equals -3, we will find a vertical asymptote. -3 is the value that makes this factor equal to 0, but it doesn't cancel, so I end up with a number divided by 0, which is why we see this spike off to infinity in one direction or the other. Okay, so hopefully that was a good overview and you'll be able to tell these apart. Notice you have to factor the bottom to be able to do any of this. All right, so if we're given this equation here, can we create a reasonable graph of this? Okay, there's a few features you get for free when it's not in factored form, but rather in standard form. One is right here, we get the y-intercept. The y-intercept is when x is equal to 0. So if x is equal to 0, all of these terms will cancel out. And I'll be left with just the constants at the end. Negative 3 over negative 1 gives me a y-intercept of y equals 3. All right, we'll talk more about end behavior in a second, but the fact that these degrees match means that the end behavior will be a horizontal asymptote, and it'll be at the ratio of the leading coefficients. So it's going to be at y equals 2 over 4, which equals 1/2. We'll talk more about that in a second. All right, in order to get other features though, I'm going to have to factor this. So we got to factor the top and the bottom. Let's do that down here. So on the top, I can try and do a version of simple factoring, but where I put a 2x in so that I can avoid having to do factoring by grouping. And I got to think of two numbers that multiply to be negative 3. But one of them is going to get added to 2 before, or multiplied by 2 before it gets added to the other. So there's not that many things that multiply to be negative 3. It's got to be a negative 1 and a 3, or a negative 3 and a 1. So we can try to just put those in there until we can get an x here. And let me see, we're going to want, let's see, that we don't want to get a 6. So we probably want this to be the 3, and this to be the 1. This one will get multiplied by 2 before getting added, so we probably want this to be the negative and this to be the positive. All right, let's try foiling that out. We get a 2x squared plus 3x minus 2x. That does give us our x minus 3. All right, and on the bottom, let's see, we could split this into a 2x and a 2x, or a 4x and an x. This one we might want to do factoring by grouping. So I multiply a and c off to the side, negative 4. Two numbers that multiply to be negative 4 but add to be negative 3 are a negative 4 and a 1. Split that middle term, make it 4x squared minus 4x plus x minus 1. Regroup, take out the greatest common factor of a 4x, leave behind an x minus 1 and a 1. Leave behind an x minus 1, which gives us the factors 4x plus 1 and x minus 1. Okay, let's just double check. We got a 4x squared minus 4x plus x. That's going to give us our negative 3x minus 1. Okay, so let's lightly draw that these two are crossing each other out. But now, what feature is that going to cause? Well, because these cancel it out, there's going to be a hole at the value that makes this equal to 0. So there's going to be a hole at x equals 1. All right, and now this factor doesn't cancel out, so it's going to cause a vertical asymptote. And figuring out where that's going to be, maybe we can set that equal to 0 and solve. Get 1 equals negative 4x. So negative 1/4 equals x is our vertical asymptote. So at x equals negative 1/4. All right, and then sort of as a bonus, we can also look at the factor on the top that didn't cancel. This is going to cause an x-intercept. And it's going to be at the value that makes that equal to 0, which is x equals negative 3/2. So x equals negative 3/2. Okay, so let's see if we can put all of this together into a single graph. We're just going to do a rough sketch of that graph. So let's have xy axis. Let's use dotted lines to represent the asymptotes for this function. X equals negative 1/4 will be very close to that x-axis. and y equals 1/2, just above that y-axis. So those are kind of our guiding lines. They're not part of the actual function itself. We know, now let's add in our intercepts, the x-intercept at -3/2, so we're going to cross the x-axis somewhere over here. And our y-intercept was 3, so we'll cross somewhere up here for that y-intercept. All right, so our graph wants to stay close to this end behavior asymptote until that wall gets in its way. It's going to hit this point here before going down to -infinity, reappearing at +infinity, hitting this point, and then resuming its life trying to stay close to that horizontal asymptote. Now the one thing we're missing is that hole at x equals 1, so we'll go to 1 on our x-axis, go straight up to our function, erase a little piece, and then put a little circle there just so that we skip a value. Okay. Here is the factored form of the do now. I think that is. Yes, that's looking like it's matching. Okay, can we talk about all the features of this graph? So the x minus 1 will cancel, giving us a hole at x equals 1. This doesn't cancel, so x equals -5 will be our vertical asymptote. Right up here, this gives us an x-intercept of -2. If we go back to the original unfactored form, we can see our y-intercept will be at 4/5, and our horizontal asymptote will be at 2/1, or just 2. So 4/5, 2/1. And horizontal asymptote at y equals 2. All right, so that's a lot of information. Let's see if we can put it all together into one graph. So, coordinate plane. Horizontal asymptote at y equals 2. Vertical asymptote at x equals -5. X-intercept at -2. Y-intercept at 4/3, which would be above this line here. -2, well, okay, one second. It would be below that line. 4/3 is below 2. Because, yeah, there's no way to get from a point here to over there. So that makes a little bit more sense. And now we curve in here to corner number 2, and then down here to corner number 4, hitting those 2 points on our way. And we've got a hole at x equals 1, so at 1 we'll erase a little value, draw a circle to show that we skip a value right at x equals 1. All right, and that's right at -2. You can label a few more things if you wanted to. All right, now let's talk about those end behaviors. So, different types of end behavior. So, we'll just do examples that aren't really true examples because I won't write all the numbers. But if I have something like this, x to the 3rd over x to the 4th, if the degree on the bottom is bigger, so this might just be our biggest terms, maybe there's some more terms, so a little ... after them. But these are our biggest terms. If the degree of the bottom is bigger, we're going to have a horizontal asymptote, and it's always going to be at y equals 0. And the reason for this is we'll have this number will always become the biggest number, and if we just have a slightly smaller number divided by a bigger number, as that gap becomes bigger, this will approach 0. All right, next option is we have something like this, 2x to the 5th over 3x to the 5th, and then there might be some more terms, but these are the biggest terms of the polynomials that make up the top and the bottom of this rational function. This is going to be, so now we've got equal degrees, leading towards a horizontal asymptote. But this time it's at y equals 2 over 3. If the degrees match, neither will become like so much bigger than the other one. They'll both become big at the same rate, and what will matter is the ratio of their coefficients. So that 2 over 3, we say that's the ratio of the leading coefficients. Write that down. All right. Next possibility is y equals something x to the 4th dot 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 over something x to the 3rd dot dot dot. Here, the degree of the top is 1 more than the degree of the bottom. And this is going to lead to a slant asymptote. There we go. All right, and we'll find the actual equation of that by using long division. Now you might ask, well, what if the degree of the top is like 2 or 3 more than the degree of the bottom? Then we go back to our typical polynomial end behaviors like up, 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 down, down, up, down, down, but we won't worry about those ones this unit. All right, so let's find the equation of this slant asymptote. This is an easier case because we should attempt to factor this first and just see what happens. Two numbers that multiply to be -5 but add to be 4 are going to be x plus 5 and x minus 1. But because this is over an x plus 5 and these cancel out, the equation of our slant asymptote just is the equation of the line, y equals x minus 1. And it still is considered a slant asymptote even though this isn't a case where our function just approaches this line forever. This is the line of our function. The only thing is it would have a hole at -5. So the degree is 1 more up here, and this is our equation of slant asymptote. Also is equation of the line. But because it came from a rational function, it's still considered a slant asymptote, even though it's not really a proper asymptote. It's not a straight line that our curved line approaches forever, but this is sort of a gray area, and this would still be considered the equation of our slant asymptote. All right, now here's the harder case. Factoring this one isn't going to help us, so what we have to do is we have to use long division. How do we set up long division? You put the top underneath the long division symbol, you put the bottom out in front. Then you get tunnel vision. You only focus on our biggest terms and you ask yourself, what do I have to multiply x by to get a 2x squared? Well, I have to multiply it by 2x. 2x times x becomes a 2x squared, but I also have to multiply it to this -2. I get a -4x, and then I got to subtract this away. So -3 minus a -4 is the same as -3 plus 4. This becomes just a 1x. I can drop down the +3. These terms cancel, by the way. And now again, I get tunnel vision. What do I have to multiply x by to get an x? Well, just a 1. And at this point, I can stop because this is now a linear equation. This is our y equals mx plus b. So this just becomes y equals 2x plus 1. So we stopped when we got our linear equation. So when you have M and B. In slant asymptotes, when you do the long division, it always stops after just 2 steps, because the first step gives you the slope, the second step gives you the y-intercept, and you don't have to keep going with that long division. So you set up the long division, that's kind of hard, but it doesn't take as long to evaluate because you get to stop as soon as you reach this point. So what would happen if I actually graphed that function and its slant asymptote? I'll just show you. It looks like this. So the blue line is our actual function, and the red line is the slant asymptote that this blue line is trying to approach at the ends. And then there's a vertical asymptote in there getting in its way. That vertical asymptote has got to be located at 2 because this is the factor that doesn't cancel. And that's about what it looks like. All right, I'll embed a few more questions here. That's that for this lecture video, and have a good rest of your day.